Let's do an analysis of the all-important dipole in an electric field. Here's the electric field, and there's the dipole. All right, with that almost orchestral introduction, here is the electric field. We have negative and positive Q. So a dipole has an overall charge that's zero, but it has polarity. Right, so i.e. the water molecule. So we have equal and opposite charges on both sides. Well, in this electric field, we know the force on the positive is going to be to the right, because by definition, an electric field is the direction of force on a positive charge. And then the negative has an equal force to the left. And they're separated by distance d. We know that the sum of the forces is zero. There's no translational acceleration here. But the torques, it's a different story, because we have a moment arm through which these forces act. So it's the clockwise plus counterclockwise torque. This force on this charge tries to rotate it clockwise. This one tries to rotate it clockwise. So there is no counterclockwise torque. All right, so a little geometry here. This is d sine of phi, with phi being here. Now we could think of this as pivoting about the center point here. And so this is d over 2. So we got a torque twisting clockwise over here. And from this charge, likewise, the same thing. So we could say it's QE, that's the force, times d over 2 sine of phi plus QE d over 2 sine of phi. Or just pivoted about the negative charge right here, which is kind of how the geometry is set up here anyway. So rotated about this point, and we just have torque is QE d sine of phi. All right, then this QD is going to get its own special name. It's very special today, so we're going to call it the electric dipole moment. And the symbol is P, and I'll try not to express it as rho, since we use rho so often. And by the way, we're not done using the symbol rho for different physical quantities. But that's another story. So this is charge times separation. If you think of P and the electric dipole moment, it's the product of charge and separation distance between them. So both of those concepts together have this intuitive feel for twisting force, right? Well, the vector direction of this P is along the dipole axis from the negative to the positive charge. So here it is. That's the direction that it is oriented. And if you notice, it's being this whole system is trying to rotate clockwise. So it's trying to rotate P to become in line, to come into alignment with the external electric field. So PE sine of phi, which is the torque on a dipole, P cross E. And again, the torque is always trying to align that dipole moment with the external electric field. Now let's consider the torque and the work and the potential energy associated with the dipole. Well, if you consider what the torque is doing here, is trying to reduce the angle. So we're going to call this torque being minus PE sine of phi. And the work done by the E field then, well, dW is torque d phi. We've learned that before. And so the work is just the integral of the torque with respect to the angle. Now when the torque does positive work, when you do positive work, it's going to decrease the potential energy. Same thing that happens in our gravitational analogy. So the work done then is the integral from first angle to the second angle of the torque with respect to phi. So that's PE cosine of phi from phi1 to phi2. So gives us the difference in the cosines times PE. Now work is negative change in potential energy. It's electric potential energy in this case. So that's U1 minus U2. So U is minus PE cosine of phi, because you see in the work done that we have the two terms, PE cosine of phi 2 and cosine of phi 1. So those are just the potential energies at the given positions, theta 2 and, I'm sorry, phi 2 and phi 1. The negative thereof. So the potential energy is minus PE cosine of phi. And this vector times the cosine of phi times this scalar is, I'm sorry, they're both vectors. This vector times this vector, cosine of phi, is the electric potential energy of the dipole, being minus P dot E. So we have this astoundingly exciting expression, potential energy is minus P dot E. So let's make some sense out of that. Put some E field on its skeleton. All right. In this configuration, we notice that the dipole moment points in the direction of the electric field. And this is actually the minimum potential energy. If you think the forces on this way, the forces on this one is the opposite way. It's in stable equilibrium. It does not have anywhere to go where the energy would be less. So it's minimum potential energy, and that is minus PE. Now, that's with phi is equal to 0. So, how about in this configuration where we have the thing rotated 90 degrees, the electric dipole moment is at pi over 2. So minus PE cosine of phi, cosine of pi over 2, 0. So that is certainly more energy, potential energy, in this configuration. We call it 0. That shouldn't surprise you too much, especially after rattling your brain with the whole concept of the gravitational potential energy out at infinity being 0, or its maximum. Finally, then we have the maximum potential energy configuration, where the dipole moment is at angle pi, and so that's minus PE cosine of pi, which is positive PE. So we see the total amount of energy change from lowest to highest is just twice PE in this case. Well, let's do an example problem, straightforward, with just charges and forces. So we have a couple of charges hanging by a thread. Mass M, charge Q, length L, small angle phi, that they are displaced from the equilibrium. And our job is to find that separation distance where they are in equilibrium. The electric force is K QQ over d squared. The gravitational force is mg. Here's the radial part. Here's the restoring part, the tangential part. And that's mg sine of phi. So mg sine of phi is what is going to fight the electric force. So for small angles, Fe, mg sine of phi, which is mg phi, because sine of phi and phi are approximately the same. So that's the repulsion, force, balance, and gravity. Then k q squared over d squared equals mg phi. Recognizing that the separation distance d is twice L sine of phi, so L sine of phi, but sine of phi is phi, so 2L phi, therefore phi is not phi phi, but d over 2L. And thus we have mg phi is mgd over 2L. Now we can take the d squared and bring it up over here to mgd, getting mgd to the third power, which is q squared L over 2 pi epsilon 0. So the distance is the cube root of q squared L over 2 pi epsilon 0 mg. And that should have been very satisfying. Let's do this fairly interesting problem, where we have 2 point charges, Q and Q, that are fixed in place, and little q here is going to oscillate back and forth. It's got mass m, And the position x from the equilibrium, x is here, is very small compared to a, so it's just oscillating back and forth in a small region. So this is going to be an approximate solution to determine the frequency of oscillation. And one of the reasons for this, you can probably kind of figure out, if we go really close to one or the other of the fixed charges here, the dominant force is going to be from that charge, and it's an inverse square law, and it's just going to change the nature of the problem. But we're going to use the binomial theorem to get a good solution for this problem when x is much less than a. So let's figure out the frequency of oscillation. Force on the charge is EQ. E field times charge, which is K. Now, the force on this charge, K, Q squared over Q, all right? Q times Q over A plus X. So this is the distance A plus X to the right. That's the distance, square that. And now opposing that to the left is the force of this big Q on little q, pointing to the left, so we have to subtract off QQ times this distance, which is A minus X. So there it is. Now we're going to help ourselves by multiplying the denominator by A squared over A squared. The top A squared here will factor out, and we can put it right over here. The bottom A squared will go inside here and divide this A out. So let's go ahead and do that. So there's the first A squared factored out in the denominator. And here's the effect of the second one. All right. Now that'll actually help us momentarily. We can factor out QQ. Let's go ahead and do that. QQ over 4 pi epsilon 0 A squared times 1 plus x over a to the negative 2 minus 1 minus x over a to the negative 2. We have this binomial expansion now where 1 plus z to the n equals these terms, 1 plus nz plus n minus 1z squared over 2. The binomial terms diminish in their importance very rapidly, so we're going to apply the first two terms of the binomial expansion to both of these terms here. So that's what we're going to do. We're going to apply where z is x over a, well, x over a minus x over a, and n is negative 2. So let's go ahead and apply the first two terms to these two terms and see what we get. All right, so here's our expression. Here's the physical situation. And so we have QQ over 4 pi epsilon 0 a squared. Now applying the binomial expansion to this term gives us 1 plus minus 2 x over a. Negative 2 is the n. This is z. And then we're going to subtract off this term expanded, which is 1 plus negative 2 times negative x over a. All right, well, these negatives take care of each other. So this simplifies to, and the 1's go away. So minus 2x over a, the 1's gone here. This is plus, so you have a minus for the whole thing. And it's minus 2x over a, so that gives us minus 4x over a times the piece out in front. The 4's divide out here, and so we can express our force acting on this little charge from the two big point charges as minus QQ over pi epsilon 0 a to the third x. Now you'll recognize that this is a constant. So if f equals negative kx, that is the condition for the harmonic oscillator. So we do have simple harmonic motion approximated for a small x. You might also recall that omega squared is k over m. Therefore, k equals m times omega squared. That's this term, m omega squared. So what we're going to do is now recognize that omega is 2 pi f, and that is the square root of this whole thing. But we have to divide by m because m omega squared. This is not just, here's omega, and you have to divide through by m and take the square root. So there's divided by m, and there's the square root. All right, enough said about that. Our final answer is, and a very beautiful expression of physics it is.